Welcome to a podcast on the Bag A, Bag B example. Okay, so let's take a look at the example from the textbook about what is in the bag. All right, so we're given the situation where there are two bags, we call them Bag A and Bag B, and each bag contains 20 vouchers of the same size and shape. The contents of each bag in terms of the face value and the frequency of the voucher values is described below. So what we're given here are two frequency tables, a frequency table here for bag A and another frequency table here for bag B. Now, while these frequency tables are really nice, they can be somewhat a difficult way of actually looking at the contents of the bags. So in a minute what we're going to do is take a look at the contents of the bags via a frequency plot, okay? But just let's take a quick peek at what we can see this in the bags. What we see here in bag A, we've got a negative $1,000 voucher in bag A. There's only one of those. There's seven $10 vouchers, six $20 vouchers, two $30, two $40s, $150, and $160. Over here in bag B, notice that there is one $1,000 voucher. There are seven $60 vouchers, six $50, 40 of the twos, 32 of the, two of the 40s, two of the 30s, one of the 20s, one of the 10s, okay? So if we take that information and we plot it by putting the value of the vouchers on the x-axis, that's going to be our data axis, okay? And putting the height or the frequency along the y-axis will create what is referred to as a frequency plot, okay? So let's do that. And notice that we've now created a plot for bag A and a plot for bag B. And notice that just like we had with the chart, notice that we can count the frequency or how often each of the vouchers appears by counting the number of x's that we stacked over the particular value of the voucher. All right. So we'll come back to this plot a lot in just a minute here. Okay, so here's the problem. You're going to be shown only one of the bags, and you'll be allowed to gather one piece of data from it. We then have to decide whether to keep or reject it. If we keep it and it's bag A, we need to pay $560. If it's bag B, we win $1,890. All right? So based upon these distributions that we just saw here, these frequency distributions, we're going to try and come up with some sort of a decision rule to decide upon whether we want to retain the bag or we want to give it back. So before we go any further with this, though, we're going to have to set up our hypotheses. Our null hypothesis is going to be that the shown bag is bag A. That's the bad one. That's the one that we end up owing a bunch of money, $580 roughly. The alternate hypothesis, which is the hypothesis we're hoping is true, is that the bag they gave us was bag B. If it's bag B, then we win about $1,800, right? So, draw one voucher. How are we going to decide which bag it is based upon the single voucher that we draw? Okay? Well, we're going to create what's referred to as a decision rule. Now, this is the textbook's formal definition of a decision rule. Say formal here again, when we say a formal rule that states, based on the data obtained, when to reject the null hypothesis H sub O. Generally, it specifies a set of values based on the data to be collected, which are contradictory to the null hypothesis and which favor the alternate hypothesis. Now, that's quite a mouthful. Let's see if we can maybe kind of simplify that just a bit. More basic, what we're going to do is assume the null is correct. We'll collect data. If the data collected is very unlikely to have occurred in the distribution of the null, but is likely to have occurred in the distribution of the alternate, then we'll reject the null hypothesis, okay? So we're back to that definition that we had early on in the course about what do we mean to be statistically significant. We're saying it's very unlikely to occur given the null was true, which means in the distribution of the null, then we'll reject the null hypothesis, okay? But notice by saying that, we're also going to say that it was likely to occur in the distribution of the alternate. Okay, now we got one more idea that we're going to need to tie in here from an earlier discussion. That was example 1.1, and that's direction of extreme. Now, the direction of extreme corresponds to the position of the values that are more likely under the alternate hypothesis than under the null hypothesis. If the larger values are more likely under H1, then the direction of extreme is to the right. So what we meant by that, let's just refresh our memory here for a second, is that if the null distribution, if the bulk of the null is here, let's just say HO is here, and the bulk of the alternate is over here to the right, okay, then we notice that we're one direction, one-sided direction of extreme, and in this case it's one-sided to the right. All right. Okay, so let's go ahead and come up with a decision rule. Decision rule we're going to roll with is we're going to say we'll reject the null hypothesis if the selected voucher is $60 or $1,000. That is, if the voucher is greater than or equal to $60, we'll reject the null hypothesis. Okay? Now let's think about that for a second. That makes a fair amount of sense here. If I grabbed a $60 voucher, that's a really unusual event coming out of bag A, right? In other words, $60 here, not going to happen very often. On the other hand, a $60 voucher happens fairly often in bag B. So if I grabbed a $60 voucher in my single draw out of the bag, a safe bet that I've got bag B. Now, let's look at it a different way. What if I pulled a $10 voucher? Well, if I pulled a $10 voucher, probably the safe bet would be that I have bag A and not bag B, okay? Now, the thing to notice here, though, is that if I pulled a $60 voucher, I'm not 100% sure that it's bag A, am I? That it's bag B. I could still be in bag A, because notice there is one $60 voucher in bag A. And likewise with the $10 voucher. If I pull a $10 voucher, right, I'm not 100% sure that I'm in bag A, because notice there still is a $10 voucher in bag B. If I pull the $1,000 voucher, though, I definitely know I'm in bag B. Or if I pull the negative $1,000 voucher, I know I'm definitely in bag A. All right? Okay. So what we're going to do is we're going to go see if we can calculate the probability of making a type 1 error or the probability of making a type 2 error based upon this decision rule. Okay? So a couple more definitions before we do that. First of all, when you make a decision rule, you're creating what are referred to as a rejection region and an acceptance region in the null hypotheses. So the rejection region is the set of all values that cause you to reject the null hypothesis. The acceptance region, obviously, will be the set of values that cause you to accept the null. And the critical value, which I'm just going to start abbreviating CV for these examples, what the critical value does is it demarks the region of rejection. In other words, it marks the start of the rejection region. So the critical value can be thought of as the first value in the rejection region. Okay? So let's go back to looking at type 1 and type 2 error. So if we want to look at type 1 and type 2 error again, remember what it was. Type 1 error was to reject the null when in fact it was true, right? So that's reject. A few of the letters in here, don't I? Here, let's just erase that for a second. Let's start over. That's why you work in pencil, right? So you need to reject, there we go, Mike. Reject HO when it's true, right? Okay. Type 2 error was to do what? Type 2 error was when you rejected the alternate H1 when in fact it was true, okay? So those are the two definitions that you should have pretty much top of your head right now of type 1 and type 2 error. Now what we want to know is what is the chance of making a type 1 error and what is the chance of making a type 2 error. Well, to do those calculations, we're going to take a look at our distributions accordingly of bag A and bag B. Now look, if we're going to make a type 1 error, notice that can only occur when what? When the null is true, because that was rejecting the null when in fact it was true. Well, check out, when can that happen? Well, let's say I was holding bag A, okay? If I was holding bag A, all right, and I grabbed a $60 voucher, what would I do? Well, I would reject the null hypothesis, wouldn't I? And I would accept that I'm actually holding bag B. So every value 60 up to 1,000 is going to cause me to reject the null hypothesis, okay? So what is the chance of making that error? Well, the definition of that, hopefully you realize from the reading, is we define that to be alpha, okay? So what is that probability? Well, there are 20 vouchers in the bag. There's only one $60 voucher. So the probability of making a type 1 error, or alpha, with this particular decision rule is going to be 1 out of 20. Okay? Well, what's the probability of making a type 2 error? Well, recall from the reading that the definition of a probability, the symbol that we use for type 2 error is beta. Okay? So how do we calculate beta? Well, beta happens when what? Well, say I'm holding bag B. In other words, I know that the alternate is true. If I'm holding bag B and I grab a $40 voucher, what am I going to do? Well, I'm going to reject that it's bag B and accept that it's bag A. Okay? Just quickly fill in a few gaps for you here. This region right here where type 1 error is, that's my rejection region for the null, and this is my acceptance region for the null. Okay? Well, notice the acceptance region for the null is going to lead to a rejection region for the alternate over here, right? And an acceptance region for the alternate. Okay? So what's the probability of making a type 2 error? What's the probability of rejecting the alternate when in fact it was true? Well, if I pull a $50 voucher, a $40 voucher, 30, a 20, or a 10, while I'm holding bag B, I'll reject the alternate and accept the null. So beta rolls that way, and I've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So beta turns out to be equal to what? 12/20ths. Hopefully that's all making perfect sense at this point. There's a lot of material going on here, but I think if you do go over this a couple times, it's going to start clicking for you. Okay, so another way we could consider looking at is go back to our frequency charts that we started off this whole discussion with. So notice that what I've done is I've taken my frequencies and I've turned them into fractions. In other words, 1/20, 7/20, etc. gives me the proportions of the vouchers in the bag out of 100%. So notice my shaded region right here is alpha, which is my 1/20th. My yellow region over here, my yellow shaded region, is beta, which is 12/20ths. Okay? So notice that decision rule 1 has led to a probability of making a type 1 error of 5% and a probability of making a type 2 error of 60%. Okay? So if you're willing to live with that large of a chance of making a type 2 error, then you're good to go. All right? Well, why don't we take a look and see what if we can do about possibly reducing the probability of making a type 1 error. Well, to do that, what we're going to have to do is enlarge our rejection region, okay? So enlarge our rejection region, what we're going to do is say, all right, instead of just rejecting it when it's 60 or 1,000, we'll reject it when it's 50, 60, or 1,000, okay? So decision rule number 2 is reject the null hypothesis when the voucher is $50 or more. Otherwise, accept the null that it's bag A, okay? So again, let's look at it from a tabular standpoint. Let's look at the frequency chart. Notice that what we're saying now is that this is my rejection region, right? And my rejection region includes the $50 voucher and the $60 voucher, okay? So let me write that down as this is the rejection region here, okay? And this part up here is the acceptance region. Of course, all of these are referencing back to the null. I'm talking about the null hypotheses here, or bag A. So my probability of rejecting the null when it's true is 2/20ths, right? Coming over here and figuring out beta, which is the probability of rejecting the alternate when it's true, well, that turns out to be 6/20ths, okay? So notice by this new decision rule, what I've done is I've changed the probability of making a type 1 error to 10% and the probability of making a type 2 error to 30%. Now, how do you decide which of these two decision rules would be better? Okay? Before we go look at one more version, let's talk about that for just a second. Now, if you're desperately broke and you can't afford to lose any money, then the probability of making a type 1 error here may be too large at 10% for you. On the other hand, if you're kind of flush and you can lose $580 and taking a risk at making $1,800, etc., well, then maybe 10% error is not too bad. Okay, maybe that's a pretty good chance and you're willing to live with it. Let's see what happens if we change it one more time. Let's change the probability so that now the rejection region has as its critical value, in other words, it's CV, equal to $40. Okay. So if the critical value is equal to $40, let's go take a look here again. Let's go look at back at, hang on a second, I want to back up a few slides here. Let's go take a look at the picture again. Keep going back. I'll get there yet. Okay. What I'm doing now is I'm changing it to Decision Rule 3. In Decision Rule 3, just to get a graphical look at it here, is I'm starting at $40 for my critical value, so that's going to be equal to alpha, and that's going to be equal to beta. All right. The reason I wanted to go back to the graph here for just a second was to point something out to you real quick. Okay. If my direction of extreme is one-sided to the right, then alpha will be calculated in that direction. All right. So alpha, notice, is being calculated to the right in the null hypotheses. Beta, on the other hand, will be calculated to the left in the alternate hypothesis. All right, that's a real good calculatory trick and something you might want to take advantage of. Okay. All right. So let's keep moving forward here. Okay. So back up to where I was. Give me just a second here. So we're back up to Decision Rule 3. In Decision Rule 3, notice that alpha and beta were equal to each other in this case. In this case, my alpha is equal to 4/20 and my beta is equal to 4/20. All right. Now, quick aside here, just to mention something to you. It's not uncommon for folks to think that alpha plus beta has got to be equal to 1, but we can see that it's only 8/20, which is not equal to 100%. Okay. So the reason that's going to be that way is because alpha is calculated in the distribution of the null. Beta is calculated in the distribution of the alternate. Okay, so if I take beta and I add to that this chunk right here, which by the way is referred to as the power. Okay, I'm not going to talk about that too much at the moment, but if I take the power of the test and add that to the probability of making a type 1 error, that will add to 1. Okay. All right, well, that's kind of a rapid fire drag through example about bag A, bag B. Oops, what are we doing here? Go back here. So be sure and read up on this, and we'll talk to you about it all again soon. Okay.